8.1 lesson. So particles have mass and position. Obviously, they have a mass in a certain position in the universe, and their energy, not the bonding energy, just the energy of the atom or the molecule moving around, is basically described by its motion and speed. In other words, if it's going faster, it has more energy, and that's what we call kinetic energy. Kinetic is moving. And the formula here, I think, is given in the real test. They don't actually seem to test on the numbers here, but they test on the concept. And that's kinetic energy equals 1/2 the mass. That's not meters. Remember, these are the concepts, not the units. Mass times velocity squared. And temperature is, by definition, the average kinetic moving energy of the molecules. And so as the temperature goes up, the velocity goes up. As the temperature goes down, the velocity goes down. Because basically, those are kind of the same thing. The temperature is the movement. So here's an example problem that I think illustrates the point. So this is from a real test, by the way. You have a box and it has helium and neon in it. And because all these atoms, there's a billion of these and a billion of those kind of thing. Because they're all in the same box, they are all at the same temperature. Now that means they have the same average kinetic energy, don't they? Not the same speed that's going to come up. And the question is, which one tends to fit through the hole more? Which one escapes the fastest? And it's tempting to say, well, they have the same temperature, so they have the same energy, so they're going to fit through the same. But that's not what kinetic energy is. It's not just the speed, it has to do with the mass. So how are these different? Well, they're not different in the kinetic energy because I said the temperature is the same, but they are different in the molar mass, aren't they? This is 4 grams per mole. This is 20.2 grams per mole. So this is heavier by over a factor of 5. And if you're going to get the same number, but you're going to multiply this by basically 5, this has to go down. So the neon is running around at a slower speed than the helium, or the helium is going faster. If this is a smaller number, but you have to get the same answer, the helium is smaller, then this number has to go up. So the helium is going faster, which means it's taking a shot at randomly fitting through the hole more times per minute, and the helium escapes faster. Also, okay, waves. Waves have the wavelength from any one point on a wave to the repeating point, often drawn from the crest to the crest. That's the wavelength. The kind of waves we're going to be talking about are so short that they are often measured in nanometers. And nanometers is 1 times 10 to the negative 9 meters. It's a billionth of a meter. So if you see that, it is in meters, just like centimeters is in meters, but a centimeter is 1/100th of a meter, and I'm talking about billionths of a meter. They also have a frequency, and that's how many times the waves are going by per second. So this is going by, presumably, more waves per second if all the waves are going the same speed. So let's just say that the thing of the wave is going by at the same speed, but this one's bouncing faster. So this one is going by you with more waves per second, and that is the frequency. Now, the official unit is just per second. We know it's waves per second going by, but you don't write waves because otherwise the units don't work out. So we just know it's waves, and it's just per second, or it's s to the -1, which is literally the same thing. And there was a Heinrich Hertz, German scientist, and so this is called Hertz, or HZ, in honor of him. It's not anything different. It's literally just a name for that, the way joules is the name for all the units that make up the units of energy, but it's after Dr. Joule. Or a Newton is the unit of force, even though there's a bunch of stuff inside there. It's not different from, it's just another name for it. Now, the difference with light is, though, that light goes the same speed no matter what kind of light it is. And there's a whole bunch of types of, so to speak, light. Radio, microwave, infrared, visible to humans, we mean. Ultraviolet, X-ray, and gamma rays. These are all really the same thing. It's just depending on how fast they're bouncing. not how fast they're traveling through space. My point is that all these travel through a vacuum or air at the same speed. Now, technically, they go slightly slower through air than space, but if you shine a radio wave or a microwave through the same stuff, they will travel at the same speed. Also, light comes in what we call photons, which are particles, or even maybe better, packets of energy. So particles is sometimes used, but it's not a particle like a pencil is made of particles, or molecules are particles, or even electrons are particles, because electrons are a thing somewhat in the traditional sense. They're very small, even by the chem class standards, but they exist like they have a mass. You can't just get rid of them. I mean, you could destroy one, but it would take a lot of work. And they are a traditional particle. They are a thing in the universe. And photons are not a thing in the universe in the same way. If a photon hits this black pencil, black famously absorbs light pretty well, the photon literally just ceases to be a photon in every possible way. There's nothing left of it. The energy is not lost, mind you. The energy is absorbed into the paint and heats the pencil. But the idea of the photon is gone from the universe. And that's what I mean about it's not a traditional particle in the way we usually use the word particle. So I tend to use the word packet. It's a packet of energy that also, and this is a little weird, is a wave. And waves have wavelength and frequency. So we can talk about the wavelength of light or the frequency of light. And that's very valid. We do it all the time. In fact, we're going to do some calculations with it. And again, this is just the portion in a color print, this would be colored, that you are built as a human being with human eyeballs to see. So you can't see ultraviolet or infrared or any of the others. We can see only a very small fraction, really, of the total electromagnetic spectrum. Here's a pretty key. Here's a pretty key equation. This is speed of light. That is called lambda. And that is the wavelength. I would take some notes. That is the wavelength. And that is called nu, N-U. It is a Greek letter. This is not backwards H, and this is not V. I know that looks like V. It's not. It's nu, N-U, and it means frequency. So this is going to be in meters, and this is going to be in per seconds, like I said before. And that makes sense because this is the speed of light, and speed would be in distance over time. And here we get meters per second, which is our favorite units for science because it works with all our stuff like joules and kilograms and newtons and watts and so forth. I want to jump down here for a moment. Here's another famous formula which they really might bring up, which is energy is equal to, this is called Planck's constant. There was a Dr. Planck, times, and that is the same thing that is nu again. Here I wrote, this is lambda, and this is nu. It's LAMDA. And that's wavelength and frequency. Well, here's frequency again. So we can say, well, let's solve for nu here. Nu is speed of light over lambda. So let's cross out nu and put in speed of light over lambda. And now we've combined the two equations. You don't have to do it the way, but you can, in case they ask for energy of light or how much energy was given by this photon and so forth. Planck's constant is an adjustment so that we can make frequency equal to energy, because of course the number of the frequency is not the number that we need for joules. But if we multiply it by an adjustment factor, it will be equal. So that's called Planck's constant after Dr. Planck, who's very famous in physics circles. And that makes them actually be mathematically equal. And this again is the same nu as we found in there. We see here mention of Henry Hertz. That's a little funny because it was definitely not Henry. He's very German, and it was Heinrich, and I double checked. Incidentally, he proved the existence of the electromagnetic waves that were predicted, and that's why he got a unit named after him. So the photoelectric effect involves light, photo, and electricity or electrons, electric. And here's the story. So it was discovered that if you shine certain kinds of light on certain metals, you get electrons running around or even jumping off. And that's why it was called photoelectric effect. Now, everybody knew that light was a wave. I'm going to jump to the middle here and explain something about light being a wave. It doesn't really come up in the test, but it helps me explain something above. If you shine light through a slit and then let that go through two more slits, what you get is the light overlapping. And what you get is a series of light, dark, light, dark, light, dark, because light is a wave and it has an up and a down. And this is called constructive interference. I know interference, but they call it interference anyway. So I just made up a number. If this is 2 and that's 2, and they hit the wall together, where this is a 2 and that's a 2, they hit the wall at the crest of each wave, then they add up and the crest of the new combined wave is a 4. And the trough is a -4. And these two light beams will add up and be even brighter than either one of them to get apart. Even more famously, though, there's destructive interference. If these two are traveling or hit the wall where they are opposite, where this one's at the top and this one's at the bottom, then what you have is +2 added to -2, and you end up with nothing. You end up with 0. And you end up, in effect, with no wave. And this is what would happen if you made opposite waves in a pond. If you could somehow get them so that the up wave of this one was exactly in the same spot as the down wave of that one, you would get a flat spot. You can go find people on YouTube doing it. And so pretty weirdly, it's possible to get light plus light equals dark. And that is where we get the dark spots here. So in this part, they were constructively interfering. They were adding up to even brighter. And then that effect fades as these don't match up so well. They match up less and less and less until we get to dark. And then that effect fades and they start adding up better and better and better and better because they're coming in at angles to each other like this. So we get points where they add up nicely and points where they add up really, really badly. And where they add up to 0, you get dark. And that proved to everybody that light was a wave because that's what would happen with waves in a pond and so forth. So everybody said light's a wave. Great. We cracked it, they thought. However, there were experiments that used certain kinds of light on certain metals, ultraviolet light as I recall, and it had a peculiar effect. You could get electricity going around in the middle or even electrons just jumping off. Very interesting, said everyone. And so, of course, they started fooling around with that and they turned up the light. Well, light is a wave. I'm putting in more energy. So I should get more energetic electrons. The electrons coming off should be more energetic. That's not what happened. Instead, if they doubled the light, instead of getting 500 electrons, let's just make up some numbers, they got 1,000 electrons that were just exactly the same energy as the last time they did it. So the number of electrons increased, but the energy of the electrons stayed the same. And they had tried all kinds of things, and it seemed to be the same no matter what kind of light they used or metal and so forth. And they made it dimmer and brighter. And what happened was the number of electrons changed. And if you use the same kind of light, the energy of the electrons coming off was the same no matter how bright you made it. Well, this didn't really go along with their theory of it being a wave. So their experiment seemed to contradict their other experiment. On the other hand, this is pretty much a wave. I mean, that's pretty conclusive. So everybody was kind of stumped. And Einstein did sort of a mental experiment. And I'm just broadly paraphrasing, and I don't mean to use these actual words, but in a sense, he said, you know what this is like? It's like when you shoot marbles into another group of marbles. If you shoot more marbles, you get more marbles knocked out at the same energy because it's not that you shot them any harder, it's that you shot more of them. This reminds me of, say, like ball bearings hitting ball bearings or marbles hitting marbles. So what if light is a wave? I'm not arguing with your previous experiment. I understand the point. Yes, it's a wave. But I'm saying, what if it's also a particle? What if it's also a packet? What if it comes in lumps? wave lumps. What if it comes in little packets that are separate from each other? Because that would let me keep your wave experiment down here and then explain this one. So I'm proposing that light is a packet that is also a wave at the same time. And that is completely the accepted theory at this point. And if you tried to argue with that in a physics classroom these days, you would just get laughed out because it's been proven too much. And no one has any real doubt that that is, in fact, what's happening. It's sometimes jokingly called a wavicle. And that's called a photon for real, the packet of wave, so to speak, that the packet of wave, if we can say that, that light travels in. All of them, all the types of light travel in packets called photons. I describe all that because the real test might ask questions about electrons being ejected by light, and that's the kind of experiment they're talking about. So I know it helps to have a visual, and that's what they mean. And then we can say, oh, if the energy of the electron was this much, then we can figure out the energy of the light, or the other way around, because we also have this. Now, I like to solve this like this. You can hit pause and prove that I did it right. But here's how I think of it. The light has a certain amount of energy, and we'll use some dummy numbers that stand in. The light has an energy of 10. This electron, of course, is bound to the metal in some fashion. I mean, it didn't fly away already, so it must be stuck in there somewhat. And let's just say that it takes 3 energy things to break this electron loose. So you put in 10, it takes 3 of them. You got to spend it to break it loose. What's the energy of the electron? It's 7 energy things. So the light energy minus the binding energy will be the kinetic energy of the electron, which is just another way of writing this. The bottom talks about some interesting stuff. I don't know that I ever solved this. What is pretty interesting, though, I think, is the de Broglie wave. And if you figure out how I'm supposed to say that in English, you tell me. He was a French scientist, and he won the Nobel Prize for this. He said that everything, and I mean everything you've ever encountered, and I mean everything, you right now, has a wave characteristic. And I do not mean that there's like we could draw a wave because your molecules are bouncing because you're warm. I mean, the fundamental idea of matter in this universe is also a wave. And the reason you can't tell is because as soon as you get any kind of decent mass, and I mean anything at all, the wave characteristic starts to get swamped to where you can't tell anymore. And I know that you've never observed a paperclip, dancing around and acting like a wave. It's because if you find the wavelength of something this massive, it's incredibly small. You have to go down basically to the idea of an electron before the wave starts to matter. And then electrons have a wave characteristic that actually matters. And they get really weird because they are a traditional particle. Like I said, they have a mass, like the paperclip has a mass. They don't just disappear from the universe like photons do. And yet they kind of wave around because their wave characteristic actually matters. In fact, remember how this was light, dark, light, dark? If you shoot electrons at 2 slits, you know what you get? And this is really weird. You get a point where they added up, and then it fades out to a 0 where they didn't add up, and then a point where they did add up. So this is like the light, dark, light. And the only real explanation is that their wave characteristic has constructively interfered here and added up to some sort of positive, and destructively interfered here and added up to a negative. And it fades in more than this shows. It fades in and out. But you can get stripy, stripy, stripy like this using electrons, which proves their wave characteristic, that it actually matters with electrons. If you do this with ball bearings, you won't get that, of course. I mean, something, actually heavy on something that matters on a human scale, because their wave characteristic is too small to matter. But with electrons, it actually matters.